Much appreciated.
Well,
RJ, I take care of you in a moment. Yeah, don't even need to introduce this lady. Is a smooth operatress joining us from Canada. And yeah, Katarina, stage is yours.
thank you so much, Christoph. Hello, everybody. Hopefully, I'll try to keep things within schedule over here because it sounds like we're a little bit past time. So my name's Katarina. I'm one of the co-founders and directors of Voltera. I'll be telling you a little bit more about us if you're not sure who Voltera is yet, but I'm really excited today to be here and telling you about a really cool project that we've done here in-house with regards to printing ECG electrodes with biocompatible gold ink with our Nova dispensing system. So let's go ahead and jump into a little bit about us. So we've been at TechBlick many years in a row, so I'm sure many of you are familiar with Voltera right now. For those of you that aren't, just a quick background. We were founded in 2013, just kind of out of a frustration with the hardware development process. Specifically, we just wanted to empower innovators and hardware developers by enabling them to print circuit boards directly from their desktop with these desktop dispensing systems, rather than kind of waiting for weeks for their circuitry to come back in order to put it into a production environment. And since then, we've just basically been doing exactly that. We collaborate with thousands of professors, innovators, in over 90 countries to really just help break down these developmental barriers with our direct write prototyping systems. Our most recent one being the Voltera Nova. So of course, the Voltera Nova system, as I was mentioning, great with screen printable pastes, essentially, that allow you to create a prototype that's representative of the final manufactured product, which you could eventually take to screen printing and roll-to-roll production. And I was also mentioning, in case you didn't hear, another advantage of the screen printable heavy pastes is that they have very heavy metal loading. So a very high percentage, you can get up to 95% of nanoparticles or microflakes, which of course serves great electrical performance, solderability, and just great structural properties post-processing. So back to our little project over here. We really wanted to zone in on a project that had to do with bioelectronics for a couple of different reasons. I mean, the bioelectronics field is just getting started and about to explode. It was estimated to be about 19 billion in 2023, projected to reach about 30 billion by 2033, with an annual growth rate of about 17%, which is huge. The United States is anticipated to have the greatest market share, really making up about 25% of the global market alone, and driving this, of course, just significant funding from the National Institute of Health, DARPA, FDA's Breakthrough Device Program, as well as, of course, just thriving, innovation hubs like Silicon Valley, Boston. So it's really positioning the United States to be the global leader in bioelectronics, with the EU as a whole coming in as a close second competitor. So a couple more things that are really driving this market, of course, rising health awareness for personalized healthcare. That was really accelerated hugely by the COVID-19 pandemic, right? Another couple things, advantages in technologies like nanoscale electrical measurement, point of care diagnostics, and microfluidic immunoassays. And then, unfortunately, just the drastic increase of chronic diseases like heart disease and diabetes. So cheeseburgers basically can largely be contributed to this explosion that we're seeing in the biomedical device field. And then huge industry investments, like I've already mentioned. A couple of transformative applications that we've kind of seen being done with our clientele that are really exciting up and coming for printed electronics. Anything from pacemakers and sort of biosensors, all the way up to sort of brain-computer interfaces and smart contact lenses. So some really interesting and fascinating stuff that's happening, and how we expect printed electronics to be a key enabler. Essentially flexible, biocompatible materials and low-cost, scalable manufacturing, right? Make printed electronics essential for bioelectronics, especially for wearable and implantable devices. So speaking of wearable and implantable devices, we decided to take on this project of sort of creating a more comfortable ECG electrode sensor that was hugely inspired by one of our clientele at York University, who was working on these sort of biomedical tattoos for continuous monitoring systems. So a couple issues with just the current products on the market. They kind of have these adhesives that cause a lot of skin irritation. A lot of clients can actually also be allergic to some of these adhesives that come on these ECG electrodes. They require a wet electrode gel, which can dry out really quickly and kind of lead to reduced signal quality and basically unsustainable for prolonged use, which is particularly an issue for people that are faced with the unfortunate circumstance where they have to be in continuous monitoring. Signal quality issues is another one. So more motion artifacts and inconsistent kind of skin contact result in really poor accuracy, and just application removal. So for anybody in the audience that has had to take one of these off, you're basically ripping off the first layer of your skin, which isn't a big deal once in a while. But again, this is a real challenge for patients that have to have continuous inpatient monitoring of these devices. And then, of course, the last one just being the sustainability factor. So got biocompatibility and waste. Basically, these are single-use electrodes that basically just get tossed away after a single use. And of course, this remains a concern for sustainability and certain sensitive populations, right? And so we sort of aimed with the power of the Voltera Nova and different materials that we had with some of our partners to sort of create this device that was meant to be a much more comfortable, reusable ECG electrode that could function comparatively to the conventional ones on the market. And so the project was really broken out into three main components. So you had the ECG electrode that was printed with biocompatible gold ink. And this one was really designed to just attach directly to the skin for heart signal detection. Notable that this particular electrode doesn't actually require any type of wet gel to function. So it can be a dry electrode, a control unit. So this includes a heart rate monitor and the controller. And then, of course, just a 3D printed enclosure that allowed the unit to be protected from any type of physical stress. The heart rate monitor, which you see here in it's a little kind of red PCB that you see, was just a SparkFun heart rate monitor. And it basically just serves as a preamplifier, transforming the heart's biopotentials from ECG electrodes into usable voltage. And so these were the three sort of primary components when we came to print this specific ECG electrode. Getting a little bit more into the actual design of the electrode. So the research community was very helpful, as always. Now, I have the reference down here. We were looking into a study that was published in Physics Reviews, which basically identifies this hexagonal labyrinth pattern as kind of being the optimal design for dry electrodes for a couple of different reasons. So basically, this pattern offers a superior ratio of surface area to material volume. This significantly improves kind of electrical sensitivity compared to other electrode designs. The structure also allows for a high density network of conductive pathways, of course, increasing contact with the skin, and it also minimizes the amount of material, making the electrodes very efficient and cost effective as well. The design does also help in enhancing signal to noise ratio. So it leads to more accurate ECG readings, even kind of when the patient is dynamic or in movement. And it's really sort of been optimized for dry electrode geometry, right? So it really allows for that maximum sensitivity while eliminating the need for a wet gel, which, as I mentioned earlier, can cause a lot of skin irritation. And so this was the general design. There was a base layer here that was printed out of silver ink. And this is sort of that circular design that you see with the two traces coming out. And then the top, as I mentioned, hexagonal structure that was printed with biocompatible gold ink. So getting a little bit more into the materials that were used, the design was printed on just conventional TPU, which is stretchable, great for biomedical applications. And then that base silver layer that you see there was printed with a Celanese and Texar silver ink. This is a great material. We work with a ton of suppliers on the market, but we specifically love this one for its stretchability and flexibility. So it works great on TPU, even under stretching and bending. It's really great for these ideal applications and doesn't lose its conductivity under high stress. It's got that high conductivity. It's very durable. It cures at very low temperatures, so it's very suitable for these low temperature substrates. And of course, it's scalable in manufacturing as well. And then for the hexagonal pattern, we ended up using a Creative Materials 261340, I believe it was, gold ink. to print that pattern. So we scraped the market for a bunch of different gold inks out there. They tend to be very expensive. This was one of the more economical ones on the market. And again, very suitable for biocompatible applications. It's got great conductive properties. This is a flexible ink, so great for devices that are going to be flexing. Not as much stretchability as we see in the silver ink, and very easy to process. So again, just cures at very low temperatures, and it's compatible with a variety of different substrates, providing great adhesion to them. And so this was kind of how the substrate was printed out. The design was printed out. And then it went into post-processing. So after printing and curing, the electrodes were, basically we have these sort of metal snaps that were inserted into rivets directly into that silver part that was printed that you see. So holes were punched into the electrodes to establish that electrical connection. To strengthen the electrodes, we actually ended up kind of cutting out a hexagonal pattern out of PET sheets that matched that sort of hexagonal pattern, and placed them between the layers of TPU. So this basically just helped prevent the electrode from overstretching and maintain that conductivity of the gold ink. Because as I mentioned, this isn't as much of a stretchable material as it is just flexible. And then we just use the conventional t-shirt press to basically just laminate the layers together and ensure a kind of durable bond there. So with the electrodes ready, we connected them to the heart rate monitor via the sensor cable here that you can see in the final design was tested for functionality. And then just a really quick overview of the control board here. We actually used our PCB printer in order to develop this control board. And so this was just done on a conventional sort of FR4 substrate using our standard silver conductor. And then that board essentially functions to be a connection between that SparkFun heart rate monitor and the Arduino microcontroller that we use. So to mount the Arduino microcontroller and the heart rate monitor, just drill holes into the FR4 using the V1 printer. And then this really just helped with the component placement to ensure that the board was clean and organized. And then after drilling, you just print these silver traces with the V1 to establish the electrical connections between these components. And this approach really basically helps to eliminate a big wiry mess that you would see in these conventional hardware prototypes, which I'm always a fan of that, of course. Some of the challenges that we experienced while completing this project. So of course, managing the high cost of the gold conductive ink was a pretty key challenge of ours. In order to reduce waste of this precious material, we did end up validating the designs first with the silver ink before using the gold one. So always helpful to just use something cheaper. We did end up using these sort of overlapping fiducial marks to ensure precise alignment between the different layers during printing. This particular material did also have, the gold material specifically, had an issue with settling of particles. So the gold particles tend to kind of settle when stored, which could cause nozzle clogging. And in order to solve this, we did end up using our dual asymmetric centrifugal mixer to evenly just mix out the gold particles prior to printing. And then, yeah, I mean, working with gold inks, there's a lot of great properties. It does present its challenges, but with the Nova system here, it does provide very sort of precise volume control out of this precious material. And so it makes it much more doable when you're sort of working with these very expensive materials to control how much you're actually using versus how much is going to waste. You could imagine in your sort of conventional screen printable prototype, I mean, you would end up scraping quite a bit of material onto that stencils, whereas when you're using this direct write precision system, you end up using a lot less material, only where it needs to go. Yeah, the results of the actual experiment ended up being quite successful. So for this project, we did end up printing 3 electrode designs that were placed directly onto the chest for a proof of concept. And so the design was very successful. It outputted meaningful data, but it's important to note that commercial ECGs would typically have 12 reading points. So this project is not intended for any type of medical diagnosis or treatment. That's the caveat there, disclaimer. But the Arduino microcontroller did very accurately interpret heart rates and rhythm readings, ensuring the precise data was captured. So the end of the day, the printed electrodes did have comparable sensitivity to commonly available wet electrodes, while of course, offering that advantage that we were going for of not requiring the wet gel and also being reusable, right? These dry electrodes are also very suitable for screen printing in large quantities, making them pretty suitable for mass scale production. So yeah, I mean, it was a really great proof of concept, great project. The electrodes were indeed more comfortable. They were reusable at the end of the day, and they did not sacrifice the entire top layer of your skin when wearing them. So the project showed really promising results for future research and wearable electrodes, really showcasing how printed electronics can kind of help drive that. We do have a full video as well as a white paper that's available through our website, voltera.io. If you want to go and check out that video and you want to go check out the full breakdown of how this project was accomplished, I encourage you to go ahead and do that. One thing that really helped make this project quite easy was a plan feature. So a new software feature that we're calling Plan. It's launching at the beginning of next year. And essentially, it just makes multi-layer printing really, really easy to do. So as the user, they're able to load different design files for each layer and kind of effortlessly align those patterns and pair them to a specific ink, right? So generally speaking, when you're using these polymer thick pastes, each material has a very, very unique rheology, which can kind of make them challenging for consistent dispensing. And so essentially what you have to do is calibrate each material with a unique set of dispensing parameters. Now, the good thing is once it's calibrated, those parameters can actually be saved into the system and then called upon later when the material is being used for the specific layer that you're printing. So this is great. I mean, it saves you a lot of time to quickly call upon those settings for each layer and really sort of enhances the efficiency of multi-layer tray stacking and multi-material printing. This is just a quick example here of an FSR sensor we have printed with silver and carbon thick paste. More applications that please, if you have time, have a look on our website. We have countless applications we've done, including 7-layer zinc oxide batteries, flexible membrane keyboards. One of my personal favorite projects was the electroluminescent displays that we did with Cerilon's line of electroluminescent inks. Really, really great, demonstrates the potential for sort of these flexible display technologies. And then, of course, as commonly requested by a lot of customers out there, printing on fabric. So we did manage to kind of print essentially a heated glove. I mean, we're from Canada, so this is very helpful for Canadian winters. But basically, we did it by printing silver directly into cotton fabric and then kind of building up the thickness within the fibers. So yeah, really great application. And as I mentioned, we have white papers as well as videos that you can go and review on these applications and many more if you're interested in having a look. At the end of the day, our mission is really just to, well, catalyze innovation by removing barriers to entry. So we're always here to make new connections, collaborate with researchers in any of the space. At the end of the day, that's our call to action. So if anything here was interesting, please feel free to reach out. And we're really interested to see what you're doing and see if we can form a potential collaboration. A little bit more on our printing service that you can have a look at. If you are interested in having a little something printed, have a look at that. And basically just really easy. You submit your design file. We get that printed within a couple weeks, and then you can kind of test your samples to see if it meets the requirements it's looking for. So try to finish that so that we can stay ahead of schedule again. Hopefully I did an okay job. I don't know if there's any time for questions, Christoph.
Well, this is very uncommunicative last two speakers. RJ, Duff, please message me in the chat if you are in a rush or not, because then I would actually like to cover a couple of questions. Yes, we cover questions. Thumbs up, nobody's in a rush. Oh, not in a rush, we have time. Thank you very much. So we cover questions. Smooth operatress, sorry for jinxing it in the beginning. So well done. We are with Kodre. Thank you for this talk. What is the precision and the smallest dimension that can be obtained with the machine? And did you try various substrates?
Yes, we work on a variety of different substrates. I'll answer that question first. So the machine actually does have a vacuum bed inside. along with a titanium microporous plate that can be easily included and as well as removed for both flexible, stretchable, as well as rigid substrates. So we've done, I mean, our clients, not just we alone, but our clients are doing anything from PET, Kapton, TPU, PDMS, rigid substrates like FR4, ceramics, glass, organic substrates as well, Rogers materials. So it really prints on a variety of different substrates. The current space and trace that you're typically seeing right now on these machines is about 100 micron space trace. Now that, of course, is also a little bit dependent on the material that you're using, because typically we find the actual rheology of the specific material also tends to affect the resolution of the final printed pattern, depending on the spreadability of the actual material once it touches the surface. So in short, that's my answer.
Follow-up from Kodre, you said you can use thicker inks. What are the lower and upper limits for viscosities?
We've done anything from about a 1,000 upper limit all the way up to 1 million centipoise for materials. So basically, you're talking anything that could be maybe like a honey-like viscosity all the way up to like a thick peanut butter-like viscosity, just to give people a visual. So it's quite a variety of materials. The thing the system doesn't handle quite as well is essentially Newtonian-based fluids. So anything that's water-like or has a very low solid content, like under 20% silver, nanoparticle or microparticle. These materials are not compressible, and they don't tend to work as well in a direct write printing system. So typically you'd be looking at like aerosol or inkjet systems for something like that. We do work in the screen printable realm, so heavy metal loading, high electrical conductivity, high performance materials used in mass manufacturing.
Interesting that you used peanut butter and honey to compare this,
and
not maple syrup.
The viscosity numbers and units don't always give people a great visual as to what that means. So as soon as I put it in food terms, you get a better understanding.
We have a question, not sure, or another Reza now. You might have covered this, but I asked again anyway. 2 questions. What is the minimum particle size of the ink? And what is the conductivity value?
The one that we used here is about 2.5 million per square was the conductivity of the actual silver conductor that we used here. Again, when we talk about the ink, I mean, we work with dozens and dozens of material suppliers from all around the world. And we go through a process where we vet the materials, we test them, and we see if they qualify to work well with our system. So materials will range in properties, conductivity, and general structural properties as well. We work with carbon, gold, silver, copper inks, a variety of them really. The same is true for particle size as well. So typically the materials in this space, we're talking microflakes, but we do also work with materials that are in the nanoscale as well. So.
Good. Oh God, Kodre, follow up. Does this affect drying?
Drying. So these, depending on which material you're specifically using, these tend to be materials that are either thermally curable or UV curable. So they usually require a UV curing oven. Some of the materials that we used here, you're talking about 200 degrees Celsius, cured for about a 10 to 20 minute period. You also do have, as I mentioned, UV curing or flash curing materials as well that require a UV curing system in order to cure them as well. So the drying time and the curing really depends on what material you're using at the end of the day.
Katarina, thank you very much.
So much. Thank you, everyone.
And yeah, hope to see you soon at live events, hopefully on-site events too.
I hope so.
Very good.
Yes, my email is here, so if anybody wants to reach out, please feel free to reach out to us directly and check out our website if I didn't answer any questions in this presentation, okay? Thank you so much, Christoph. Bye-bye.
You're welcome. Bye. If somebody wants to get in touch with Katarina, you can also email us, of course, and we facilitate.